Okay, for the lab 1, I tested the Newton's second law, especially the constant velocity and the motion of the mass and how they interact with each other. First of all, I used the table tennis ball to create a video of how the ball rolls through the flat surface. I set up the axis to see how the ball moves through the plane, and the scale is 4 centimeter, which is diameter of the ball, and we'll use that to see how the difference in the length of the ball's movement is. So I'll show you the video. As you can see, the red dots are the center of the mass of the ball, which calculates the position, which records the position of the ball in the tracker. There's time and the x. We won't use the y because it is irrelevant. Ball is moving in the x-axis. So with these two data, I put it in the spreadsheet. One is the experimental position, and one is the model position, and velocity and the velocity. So blue is the experimental. So blue position I got from the tracker, and the red model position I calculated. So for the blue part, the experimental position is the tracker one. So the experimental velocity I calculated by using the formula V equals final position minus initial position over final time minus initial time, which is delta P over delta T. I calculated the delta X first, and then delta T, and then use that to just divide those two to calculate the experimental velocity. And with the experimental velocity, I took the average of it and used it as the model velocity, which is constant throughout the motion, because according to the Newton's second law, the velocity doesn't change if there is no net force acted upon the system, right here. And because in ideal condition there is no net force, the velocity is final velocity is initial velocity because this becomes 0. So therefore, with this constant velocity, I calculated the model position using the formula R final equals R initial plus V average times delta T. Delta T is right here, velocity, and the initial position was same as the experimental position. And with that in mind, I crafted the Python file, which I'll test briefly. The initial position was this, which is this. Initial velocity is 0.685. This is centimeter and this is meter, so that's different in the point value. And the delta T is 0.03, and the video lasted for 1.5 seconds, so I set it up like that. The first is 0, and this is Newton's second law, and that's the same formula as this. So when I run this, you can see the graph and the motion of the ball, like that, same as the tracker. And the graph, I compare it more specifically. As you can see, the experimental position and the model position slightly differs, because in the model position, the force is 0, therefore making the velocity constant, which is the slope. And in experimental position, the slope changes, the velocity changes, so it is slightly off. This is more apparent in the velocity versus time graph right here. As you can see, the experimental velocity drops dramatically while the model velocity is constant. This is, in my opinion, because of the external force acted upon the system while I do the experiment, such as the friction or air resistance that causes the ball to slow down. So, in conclusion, I stated that Newton's second law is consistent and the velocity is constant unless there is external force acted upon the system. So, if there is external force or net force in the system, then the velocity changes, but if there's no net force, then the velocity is consistent or constant. Thank you.